This is the solution to example 8 from notes 3.4. And in the next few examples, we're going to write polynomial functions given zeros and other characteristics. And we need to use some of our knowledge that we've discovered in this unit. So we know that the number of zeros, counting repeated zeros, the number of times they appear, of a polynomial function is equal to the degree. So if it's a fifth degree polynomial function, we will have 5 zeros. They don't all have to be unique. In addition, we learned that for polynomials with real coefficients, irrational zeros like a plus rad b or a minus rad b, and imaginary or complex zeros such as a plus bi and a minus bi always come in conjugate pairs. So if we're told, for example, that rad 7 is a 0, we also know that its conjugate, conjugate, which is negative rad 7, will also be a 0. And we're going to combine this knowledge with our knowledge of end behavior, the leading coefficient test, to be able to write polynomial functions. So let's try example 8. So we're told that there's a polynomial function. We want to write one of least degree. That means we'll have each 0 occur the minimum number of times that it needs to. So for example, if we have a 0 where x is 2 and the multiplicity is odd, we'll just make the multiplicity 1. If the multiplicity being even, we'll make it 2 as opposed to 4 or 6 or 8. Okay, so let's try it. So we're going to say f of x is going to be, we have a leading coefficient of 1, so that's a is 1, and then we have a 0 at negative 2. So that means this 0 at negative 2 means that we're going to have x plus 2 as a factor. And then we know that 3 plus I is a 0. If 3 plus I is a 0, then we also know that its complex conjugate, 3 minus I, is also a 0. And now we'll continue writing a factor for each 0. So we will have a factor at x minus 3 plus I and x minus 3 minus I. So we always have factors of the form x minus the 0. And now we will start expanding this polynomial. So first thing that I'm going to do is I am going to distribute the negative with these complex zeros. So I'm going to write f of x is equal to x plus 2 times x minus 3 minus I times x minus 3 plus I. Now I'm going to use the associative property. I'm going to group x minus 3 in both sets of parentheses here. And the reason I'm doing this is that will give us a difference of squares pattern. Remember, if we have a plus b, the quantity, times the quantity a minus b, that's equal to a squared minus b squared, which is exactly what we have. In this case, x minus 3 will be like our a, and I will be our b. So this is a shortcut method to expand this polynomial. So we'll have x plus 2. So because we have a difference of squares, x minus 3 minus I times x minus 3 plus I will be x minus 3 squared minus I squared. So we'll continue on. So x plus 2, x minus 3 quantity squared. Squaring a binomial, we get a perfect square trinomial. So it's x squared minus 6x plus 9. And remember that I squared is negative 1. So this is minus negative 1. So now we have x plus 2 times, I'm going to combine 9 minus negative 1. I'm going to write that as 10. So x squared minus 6x plus 10. And now let's multiply x by everything in the all the terms in the second set of parentheses and 2. So we'll distribute in. So we're going to get x cubed minus 6x squared plus 10x plus 2x squared minus 12x plus 2 times 10 is 20. And now we'll combine like terms. So we'll have x cubed negative 6x squared plus 2x squared is going to give us negative 4x squared, and then we have 10x minus 12x. 10x minus 12x is minus 2x, and then we have plus 20. So the polynomial function that meets these criteria with least degree, leading coefficient of 1, and the given zeros is x cubed minus 4x squared minus 2x plus 20.